All right, so I handed out a handout from, this is in the Canvas folder for today. It outlines basically the common names that have been accepted as IUPAC names. So, and if you have questions about this, the book uses two different names to identify like an isopropyl group. It says isopropyl and then it says 1-methyl-ethyl. That violates the IUPAC rules that say you can only have one name of an alkane. And if you can name groups different names, that means there's more than one name for the alkane, which violates their own rules. So they accepted common names for the groups that are basically in gray. And so those are the ones that you're going to have to know the common names for when they're attached to a cyclohexane or when they're attached to a long chain. Okay, so those are all in one place. There's another handout that I didn't print out that kind of goes through the systematic way that we can come up with common names, which doesn't make sense because common names are just, I name something, but there is a sort of a system that they use for common names that's on there as well. So for today it was naming alkanes and cycloalkanes. And there's a lot of steps and rules for this, which is the important things to kind of take away is what steps do we use to write the names, and then how do we get those? How do we use those? So, what are your questions? Oh, and I handed out a 3x5 card. So what you can do is you can take the 3x5 card with you. There's more over there. I got more here. If you have questions that you want to bring to class but you don't want to ask them, you can throw them on the desk before I get here, or probably hand them to me since I don't know who you are yet. Then it's not like I'm going to be judging you. If you have any questions during this, you can give them to me afterwards. And what I'll do is, like on Friday, I'll sort them out real quick, and then any questions I don't get to, I'll do a quick video and put it on the discussion page. So, sorry, there you go, no problem. So then we'll do, and so then I can do that. So when I've done these in the past, I usually get inundated with questions, which is okay. I won't get through all of them in class with that, but I will put them on the discussion page and I'll let you know. And then if you need, we can come and see me or we can go back over them. So what are your questions?
Bicyclic compounds in general.
Okay, the bicyclic compounds. So basically there's a set of rules for those. And the simplest bicyclic compound that we could have is something like that. I didn't want to write that at the end. So this is a simple bicyclic molecule. If you look at this, you can kind of see that there's two 5-membered rings that are fused together that share these two bonds. And it shares these 3 carbon atoms. So if I can't do this, if I somehow put my hand over the right-hand side, you'd see the 5-membered ring. And if I put my hand over the left-hand side, you would see the 5-membered ring. So I guess I just do that. Right? There's one 5-membered ring, and then there's the other 5-membered ring. and they're fused together. So that's where the bicyclic compound comes from. In terms of naming it, we have to name it based on all of the carbon atoms that are in the molecule. So it would be like bicyclo, and then how many carbon atoms do we have total? We've got 1, 2, 3, 4, 5, 6, 7. So this is a bicycloheptane. Except in between the bicyclo and the heptane, there needs to go, there needs brackets, and there needs to be 3 numbers. And so these numbers are the number of carbons around what we call the bridgehead carbons. So these carbons right here are the bridgehead carbons. And so if we take and we look at the number of carbons, basically what we have is we have a 3-bladed propeller here. If I think of putting a line through those 2 bridgeheads, I got 3 pieces of a propeller. And the question is, how many carbons are on each one of those blades? And so here we've got 2 carbons, here we've got 2 carbons, and up here we have 1. So this would be a 2,2,1 bicyclo, or bicyclo 2,2,1 heptane.
Can you just go through that one more time?
The numbering. So again, we identify the bridge. We identify the bridgeheads. So the bridgeheads are the carbons that I don't know how. They're the bridgehead carbons. They're the ones that. Yeah, yes, except the top one kind of fuses it together too. So the bridgehead carbons are the ones that basically create, that if you have the line through it, it creates the three pieces of the ring. So then what we do is we say, okay, and if I look down on this molecule, I would see, how do I do that? We would see something like this, where we would have the triangle here, and the square here, and like the square there, and then the triangle. So we kind of are looking at it, we see it as kind of a 3-bladed propeller.
How do we assign the numbers? How do we know it's 221 and not like 122?
The convention is you start with the largest number and work to the smallest number. So in this case, we have to go 221. So then eliminating these 2 carbons, how many carbons are in this blade? So basically, there's 2 there. And then over here, there's 2 carbons, and then on this top one, there's just the 1.
So unlike the regular hexanes, they're not telling you location, they're just telling you number?
They're just telling you how to construct this. So what they're saying is, take 7 carbons, construct it as a fused system where you've got 2 carbons here, 2 carbons here, and 1 carbon here. And so you'd almost have to say, okay, I've got carbon, carbon, there's 2 carbons there, there's 2 carbons there, there's 1 carbon there, here's my bridgeheads. So I would go like this, and then that 1 carbon would be attached to both bridgeheads. Bob?
So what are those 2 in the middle? Where the top connects to it?
These two are the fused points. They're the bridgeheads.
But they're still carbons.
They're still carbons. Yeah, they're still carbons. We don't normally make these fused systems out of anything but carbons.
Okay.
So then so that's what the numbers tell us how to construct those 7. So the numbers, when you add them up, they should always be too short of the total number. So if there's a total of 5 numbers, you should have a heptane because the numbers don't include the bridgeheads.
Oh, that's what I was going to ask. If the bridgeheads are ever included.
No, the bridgeheads aren't. So if you have a heptane, you'll always have a sum of 5.
Are there always going to be 2 bridgeheads?
Not always. Well, yeah, there has to be 2 bridgeheads to fuse the system. So there would always be 2 of those. Does there have to be, for instance, you could have a 2-1-0. So there doesn't always have to be an atom in all 3 of the ring systems.
And you don't count the carbons, like in question 25, there's like a substituent. You don't count those carbons?
No, you don't count those carbons either. So substituent numbering is kind of laid out in the book in terms of, all right, let me go down. In terms of how you would do those. So let me go to full screen. So when you see, for instance, these 2 views, the left-hand view is looking down on the triangle, is looking down on the 1 carbon. We'll get to using these a little bit later on. So that's the bicycloheptane. That's the same one I just drew. And then there are others. This structure right here, if we looked at that, that would have 1, 2, 3, 4, 5, 6, 7 carbons in it. Again, but the positions are different. So this would have, let me draw that one. So if I drew that one, and then it has 1 here and 1 there. So this one is still a bicycloheptane, only in this case, the 2 bridgeheads are here. I guess the way I would identify the bridgeheads is that they're the carbons in the ring systems with 3 carbons attached. And then, so in this case, once I have that, I have 1 carbon on this side, 1 carbon on this side, and then 1, 2, 3 carbons on that side. So this would still be a bicycloheptane, but the numbers are going to change. It's going to be a 3, 1, 1, and then it'll still have heptane as its name.
How can you lane count the other one?
Which other one?
The other side.
So I counted this side, this propeller has 1 carbon, that propeller has 1 carbon, and then this propeller has 1, 2, 3. So that's where the 3, 1, 1 is. And overall we've got 1, 2, 3, 4, 5, 6 atoms, and then there's the 7th one. So this is the total number. That's the total number of carbons, and then the numbering scheme gives us how many carbons are on each side, or each, like I said, each propeller of the molecule. So the ones and the ones basically they kind of make a triangle, but they're not really a full triangle because there's not a bond between those 2 carbons. There's only the bond between those 2. So if you want to go to the numbering scheme for the alkyl, or for the ones with substituents, you don't count the substituents in the total numbers. And the reason you don't do that is because, in essence, what you have is is that it's like the parent name of the molecule, the way with alkanes. You have a parent name and then you have substituents attached to it. So if you looked at this one, for instance, for this one, if we forget about this methyl group here, if we forget about the methyl group that's right there, we would say that this has the 8 carbons in it, so it's a bicyclooctane. These 2 carbons are the bridgeheads. So on this side we've got a 2. On this side we have a 1, because we're only looking at the skeleton of the fused system. And then over here we've got 1, 2, 3 on this side. So this would be a 3, a 2, and a 1 bicyclooctane, which, thank God, is exactly what it says on the screen.
So you don't have to say like a number and then methyl, 8, methyl by, oh, okay, never mind.
So yeah, in terms of the numbering scheme,
Yeah.
what I highlighted here, even though I didn't put my initials on it, everything in red I still highlighted because I thought that gave pretty good description. So the system is numbered starting at one of the bridgeheads. So that's where I got to start numbering, is on the bridgeheads. Then you continue along the longest path, and then the second longest path, and then the third longest path. So what does that mean? That means that if I'm starting at one of the bridgeheads, I'm going to go and number the 2, 3, and the 4 to the side that has the 3 carbons. And then I'm going to number the 5 and the 6 to the side that has the 2 carbons. And then I'm going to give 6 and 7. And then, well, okay. Let me start over. Start at the bridgehead. And then we start on the side that has the most carbons. So that's where 2, 3, 4, and then you get to the other bridgehead, which is the 5. Then we go 6 and 7 to the 2 carbons, and then 8 is the last one on top with the 1. And then we look at all the groups that are attached to it, and that number and the substituent, then the alkyl group, comes after that. So in this case, the bicyclooctane means it has this entire ring system. 8-methyl means that there's a methyl group attached to 8 in the overall scheme of things.
Would you start the 1 at the other bridgehead and still follow this?
Yeah, I don't see why we couldn't. This molecule's symmetrical. Actually, if you looked at it, you could cut this molecule right in half. It would go right down the center of the methyl, and carbon 8 and carbon 3, and in between carbon 6 and 7. So whether you start here or here doesn't matter. You would get the same ones. And then it says it's important to number the bridgeheads in the direction that gives the substituent the lowest number. Well, let's imagine that you had a substituent. I'm gonna take a big chance here. I'm gonna take a huge chance here. I'm gonna put a methyl group there, because you don't know how easy it would be for me to screw this whole thing up right now, but I'll go for it. So your question about starting at the 2 bridgeheads, I have to start here with 1 and then go 2, ask me later, 3, 4, and then 5. So if there's a substituent on the chain, on the longest or the biggest, then you have to go in that direction that gives it. So in this case, I have to number 1, 2, in the front carbons because that's where the methyl group is. If I started numbering over here, 1, 2, 3, 4, then my methyl group would have a 4 on it. So I want the lowest number for the first substituent I encounter. And that's kind of like cyclohexanes, and it's definitely like the alkanes. You got a number from the end closest to the first substituent.
But like, say there's a methane group like at where the 1 is right now. So, but like the longest path still counts that, like it's more important.
Right.
Than
Right. So this one would be, there would be 2 methyls. So we would go 1, 2, 3, 4, 5. I would then if my choice, I'm going to get rid of these numbers. You may not be able to do that, but I'm going to get rid of them because they're confusing me. So there's my numbering of the scheme. Then what I'm going to do is I'm going to call this one 6, and I'm going to call that one 7. Why? Because the 1 carbon with the methyl group, I want to give that the lower number. So in this case, I'm forced to go big to small, and as I'm doing that, I'm forced to give, if 2 are tied and 1 has a substituent, it gets the next priority. So this would be a 2,6 dimethyl bicyclo-3,1,1 heptane. So, to be honest, the first couple of times you do this, or maybe all the times you do this, you might have to look at that red box in order to figure out the rules. Or what I would suggest is that you take a piece of paper and you kind of write down the sequence outside of the book, so you've got sequences to follow until you've done enough problems to hopefully then learn it. There are going to be some things in this chapter that I'm not going to require you to learn or memorize, that I'll give you a sheet for, and you'll have to know how to apply it. But we're not there yet.
What would the name of that one be?
It would be 2,6 dimethyl, and then the bicyclo-3,1,1 heptane. So in writing all these names, the parent name is what you construct first. And then for each substituent, you know what it is, and you know what number carbon it goes on.
So when you're like naming it, there are 9 carbons there, but there are only like 7 of them that aren't part of the substituent. So those are the ones that you have in the heptane, right?
There's 9 carbons. There's only 7 total. Yeah, you're right. You're 7 total carbons that are part of the parent ring system. The parent ring system is everything but those 2 methyl groups. And that's the way all naming is done. We choose a parent system, and then we have substituents hanging off of that parent system. So with bicyclics, it includes those 2 as well. So the bicyclo-3,1,1 heptane is the parent, and then I've got 2 methyl groups off of that at carbons 2 and carbon 6 is the way we would read it. David?
Did you ever have like a bicyclic substitute?
Yes, but we're going to say that's beyond what we want to talk about. If you had 2 bicyclic molecules stuck together by a carbon-carbon bond, we're not going to deal with that. But there would have to be a way to deal. There'd have to be a way to deal with that, and let's not.
Can we go over some examples of naming branched alkanes?
Yes. let me just go back here and say, now what? Stop. Okay. Slideshow from the beginning. Okay. Let me just say that, these compounds look really weird. I mean, well, they all kind of look weird at this point because we're only 4 days in. But these fuse systems, you might say, where do you find them? If I took this molecule, and I'm not going to name it, but if I took this molecule and I put maybe a methyl group here, I put a couple methyl groups there, and I put a double bonded oxygen there, I've now made camphor. I don't know if anybody's heard of camphor, but camphor is found in pine tree needles. It has a camphor-like smell. There used to be a cream that was called camphophenique. It smelled, it's almost like a methanol type smell. If I turn that O double bond C group into an OH, the molecule becomes borneol, which is also found it's found in any plant sort of extracts. In lab, we're going to take cloves and we're going to distill them to collect the essential oil of cloves. Essential oils are collected by taking plant materials and distilling them and collecting the volatile non-polar substances that come off. So you find these things in essential oils, which are the building blocks for perfumes and colognes and anything with a fragrance. And if you went and grabbed a pine needle, you would find both camphor and the OH group, which is the isoborneol or borneol. So these molecules are in nature. Plants put them together. How? You have to wait until second semester because they put them together by what are called Diels-Alder reactions. But these molecules are all over the place in essential oils. I only know that because I've had students look at essential oils using GC mass spectrometry. And when I look at the compounds, they have all sorts of these fused ring systems that I just look at and go, oh, that's cute, and then we move on. But all these fused systems, the one that I drew with the two one bridges, they're in there as well. So these compounds are made by plants primarily. So it's not they're not just, oh, you never find these things. You find them. They're manufactured by plants, and if you have a perfume on, most likely, or cologne, you're going to have one of those compounds, maybe in a small amount, but you would have one of those compounds in that fragrance. So they're in a lot of different places. So, alkanes and alkyl groups. So, these alkyl groups, or alkyl groups using the numbering system. Okay. Then okay, let's say we had this molecule. Okay. So, rules for naming alkanes. Number 1, what do we do?
Figure out the parents.
The parent chain. So the parent chain is the one that has the longest continuous carbon atoms. So let's find the chain that has the longest continuous carbon atoms. In this case, I'll give you a few seconds to take a look at that. How many carbons are in that longest chain? 9? Any other numbers? Those 9. Now, when you're looking for longest chains, there's no rhyme or reason to them. They could go left to right. They could make a C. They could make a U. They could zigzag. You just got to start at an endpoint and go until you find the longest carbon chain. So if we do that, in this case, we've got 9 carbons. So this is going to be named nonane. That's its parent name. That's the parent chain. Just like the bicyclo was the parent structure. Okay, now then we have to name, then my thing is I name the groups that are substituents. The substituents are everything else. I think the book kind of uses the term locant. It must be a Canadian thing. I've seen it, I don't like. I like substituent. Substituent's whatever's left over after I circle or highlight my longest chain. I like to do that because then it's really clear what it is. But then, if I'm starting to look at these line bond structures and I'm not quite familiar with them, I would suggest maybe putting the carbons and hydrogens in there because they may help. So every place there's an intersection, there needs a carbon atom. Every end of a line, there needs to have a carbon atom. If it's anything other than carbon, we're going to write that explicitly. So this substituent has 4 carbons. Now add hydrogens to give every carbon 4 bonds, and only 4 bonds. So a carbon with 1 bond gets 3 hydrogens. A carbon with 2 bonds gets 2 hydrogens, and a carbon with 3 bonds gets 1 hydrogen. Okay, so I like to draw the group out that way because now it can make it at the beginning a little bit easier to see. Now that group is on this sheet. But let's say that I know it's on the sheet, but I forget which one. There is a system to common names. It used to be common names. The common name system is like, I made this, I'm going to name it. If everybody else agrees with me, that's the name. There's no systematic nature to it. IUPAC is a very systematic way of naming. The IUPAC group, they sit up on the mountain and they basically decide the rules that they then pass down to everybody else. The goal being that every chemist in the world, and I suppose you could expand this to the universe if there are chemists out beyond Earth, which we'll not discuss in this class, but if there were, hopefully, because this is international, maybe interplanetary, that they would use the same rules. Of course, they're probably more advanced than us, so they probably have different rules, but that's a hypothetical question. So on the Earth, a Russian chemist, a Chinese chemist, a German chemist, a US chemist, other than the slight things for language, would name this exactly the same. If IUPAC's done their job, there's one and only one name for this. Because if there's another name for it, it's not unique. Then if I give you a name, there better be one structure you would draw for that. So that's why these rules have to be set up the way they are. So what happened? Well, what IUPAC's decided is that all the common names are now acceptable as IUPAC names. So what's the common name for this? Well, let's say I forget. In the common name system, we name this, and these are all alkyl groups because they're groups without a hydrogen. So they're substituents. That's what alkyl groups are. They're substituent groups. The total number of carbons gives you the name, the parent name. So in this case, this is a butyl group. Now, there's 4 different butyl groups. So which one is it? Well, in terms of naming the groups, if you have 4 groups in a chain, or 4 carbons in a chain, and it's attached at the end of the chain, and it's a straight chain with no branching, that's called either butyl or N-butyl. The N is optional, so you can have N-butyl or you could say butyl. That means straight chain, no branching. If it was 3 carbons, it would be N-propyl. Ethyl, there's only 2 ways to make an ethyl group out of 2 carbons, so ethyl's ethyl, methyl's methyl. And then if we went to pentyl, N-pentyl would be all 5 in a chain. And decyl would be 10 carbons in a chain. So the N term used to mean normal. And I don't know if normal chains, that's the terminology they used. The N's fallen out of vogue. I found this out in a paper when I was talking about a whole bunch of N-butyl lithium compounds that we had made, and I kept using N-butyl, and then the referee was like, we don't use N anymore, it's just butyl. And I wasn't going to argue about nomenclature, so I just erased them all and said, okay, here, accept the revision, and accept it. So I think they said it was like the. I didn't quite understand what that, having 2 thes. So butyl and butyl, they're the same. But you'll see less and less N-butyl. So this is a butyl group, but it's not an N-butyl group. So then what I tend to look for is I tend to look for a group that looks like this. A CH3 attached to a CH. CH3, CH, CH3. That in the common name is called an isogroup. So every group that has a CH3, a CH, and a CH3 is going to be called iso something. That's the one that I drew is isopropyl because it's got 3 carbons. If I added another CH2 to it, it would now be isobutyl because it's got 4 carbons. So isobutyl is the 4-carbon group that has the iso group. CH3, CH, CH3. This is an isobutyl. So then what's left? What's left is to describe the carbon that's the attachment point. And now in order to do this, I have to forget about the chain. I have to forget that, imagine I'm covering up because I'm covering it up from me, but not from you. Doesn't work that way. If I'm covering up the chain, this carbon has 1, 2 carbons attached to it. So there's a way to classify carbons according to the number of carbons they're attached to. And that's called primary, secondary, tertiary, and quaternary.
Wouldn't it be sexbutyl because they're like one of the branches to than the other?
You spoiled the fun. Yeah, it is called sec-butyl, but it's called sec-butyl because this is a secondary carbon. It has nothing to do with the branching. It just has to do with this is the secondary this is the butyl group that has a secondary attachment point. So when a carbon's attached to 1 carbon, it's primary, 2 secondary, 3 tertiary, 4 quaternary. And again, for this carbon right here, how many carbons does it have attached to it? 2. That makes it a secondary carbon. So this is called secondary butyl or S-butyl because this is the butyl group where the attachment point is secondary. Now, in order for this to be a legitimate name, there can only be one of those. Fortunately for butyl, there is. There's only one group, 4 carbons with a secondary carbon attached. And again, I don't see that other chain that this group is attached to, because otherwise that carbon would be a tertiary carbon. But I'm forgetting about the chain. I'm just looking at the group.
So do we need to know that, like, the reason it's sec-butyl is because it's coming off the secondary, or can we just like memorize the shape of the sec-butyl and be okay with that?
You could be okay with that. What I'm trying to do at this point is, let's say you want to rely on something more than memorization. Like I said, I looked at this group, I forgot what it was. So I'm trying to figure out what it is. So we can go back to basics and say, okay, I know it's got 4 carbons, so it's got to be a butyl. Which butyl is it? It isn't straight chained. It isn't an iso. So that means the only 2 criteria left are it's secondary or tertiary. So that would tell me that it's a secondary butyl. Plus also trying to give you something else other than just pure flat-out memorization. But if you like pure flat-out memorization, don't let me stop you, right? Because if that's your system, Lord knows I don't want to mess up a student's system. They've told me that in the past. Don't mess up my system. I got it down. And I'm like, no, won't do that.
Can you explain again how you go about picking whether it's like primary, secondary, tertiary?
So let's say, let me just write this group by itself. So how many carbons, forget about what's up here. What's up here is nothing, okay? So this carbon, how many other carbons are attached to it?
Are you asking me specifically?
Yeah, so how many other carbons are attached to this carbon? There's this one, right? And there's this one. And up here, that's the chain, but I don't count it.
Okay.
So I'm only looking at within that group. So it's attached to this carbon and this carbon. That means it's a secondary carbon. What's this group? What's the CH3? Primary? That one's primary because it's just attached to one. What's the CH2 group? It's secondary because it's got 2 groups attached to it. Okay. So that's how we tell if it's primary, secondary, or tertiary. Just to complete this, the last butyl group is this one. Now that's a butyl group where the carbon that's attached is what kind of carbon? It has 3 other carbons, so that makes it tertiary butyl group or a tertiary butyl group.
Is there a naming system for which way the long end of the sec butyl is going?
No, because I could reverse that. A sec butyl group looks like this with the group there. It could look like that. It could look like, and what I'm going to do is the circle is the longest chain. So any one of these 3, they're all sec butyls. So I wasn't going to mess up anybody's system when they said they were going to look at shapes, but there's 3 different shapes to the sec butyl group at least. So if you can see those are all the same shape, great. If you can't, shape might not be the best way to name this because you may not recognize the shape. They're all the same. All these carbon atoms can be moved around. So for all of these then, and there's another sheet again on Canvas where at least on paper I go through how these names sort of came about. There is a system to the common name system. The option there, the alternative is to use a numbering system with these alkyl groups. And so the numbering system with the alkyl groups would be, let's say that I did this one in the if you had these two pentyl groups, this shows the limitation. Now these pentyl groups are attached, I don't know, they could be attached to a fuse system like we started with. They could be attached to a cyclohexane ring. They could be attached to the longest chain. These two are where the common name system breaks down. Because both of these are pentyls, right? Because they got 5. But they're both sec pentyls, right? They both are pentyl groups that the attachment point is secondary, but they are not the same. Because this one is attached like at the second carbon end, and this one's attached at the third carbon end. So they're not the same. And so there is no sec pentyl group. Because in order for IUPAC to accept that, it's got to be one group for the name. So then we have to use a more systematic approach if there is no common name. And there isn't for this one, right? Everybody agree to that? If I said, well, draw me a sec pentyl group, and half of you draw me one and half of you draw me the other, I'm not a member of the IUPAC Commission because that name's not correct. It won't give me just one. So then what do? Well, then you have to go and use a modified set of rules that you would use for the straight chained alkanes. Except here, our first step is the number 1 carbon in the numbering scheme has to be the attachment point. You have no choice. Then I'm going to follow, starting at that number 1 position, I'm going to follow to give me the longest chain that I can get. So that means for this carbon, I've got a 4-carbon chain, and over here, it doesn't matter on the right-hand structure whether I go to the right or the left, I still end up with a 3-carbon chain.
Why wouldn't you include that entire top?
Because that's not the rule. The rule says I must start numbering at the attachment point.
What if it got one? What if it has one attachment point?
It can't. Because there's only this entire group can only be attached by 1 carbon to something else. So then what would we do? Real quick, this is a butyl group. The parent name of this is a propyl group. A 4-carbon alkyl group is a butyl group. Remember, these are alkyl groups. They're attached to something else. In the parent names of the alkanes, these would be butane and pentane. But there's a butyl and propyl. What's attached to the butyl group? That group is called methyl. This is a 1-methyl-butyl group. This is a 1-ethyl-propyl group. So we take the longest chain, that becomes the name of the alkyl group, and then we write the substituent and the number. And then the last thing we do is we put it in brackets, because it's got to be attached to something else, and if that number gets outside the brackets, I don't know where it belongs. So the number's got to stay in the brackets.
So what was the full name for that example we were doing earlier?
This one?
Yeah.
So this one, it doesn't matter whether I number from left to right, but I'm usually going to number from the end closest to the first substituent. I drew this dead in the middle. So this would be 5-sec-butyl nonane would be its name. 5-sec-butyl nonane. All right, obviously we didn't quite finish this up. So if you have any questions about alkanes, the alkenes and alkynes are for Friday. So that's 2 point something to 2.8, wherever we left off. So if you want to read through those. Again, while the problem's within the reading, you can try. If you have no clue and you want to now go back and do the problems after class, that's perfectly acceptable, because the problems aren't due until the end of the chapter. So if you want to read through the chapter and then go back and do the problems afterwards, again, that's fine with me. If a lot of people are doing that, or if we need to adjust the deadline, I'll adjust the deadline so the last set of problems aren't due right before class. The last class, they're due a class afterwards. If you have questions, you can email me. If you've already filled out a card, I'll take it. I've got some cards from this morning. I'll say this, even though it's not a mandate. Sometimes I do different things in the two classes. So if you go on my YouTube page, I actually did a lot more of this morning. But if you want to take a look and see, because otherwise then you're like looking at two classes and then you're like, this is too much work, I can't handle it. So I understand that, but if you want to see, I did do this morning. It's just in the YouTube page, so if you go, you can fast forward and see if there's something there. If not, ask me. I'll do a video and I'll put it on the discussion board, or come and see me and we can go over it. That includes any of the problems that from chapter 1, the moving electron problems. I already have people. I'm going to put that on there as well. Okay, so if you have questions for Friday, bring them in, throw them on the desk before I get here. Again, there's no judgment. So, but if you can write questions down, I'll go over as many as I can, and then we'll go from there. And since I've recorded this, it's going to be on the Canvas page as well.
When you write 5-sec-butyl nonane, would it go 5 dash and then a parentheses,
Yes.
sec-butyl and then nonane? Okay.
Yeah, it has to do that, because otherwise the 5's got to be outside the parentheses to tell you where that group goes.
Okay.
If there's no parentheses there, who knows what it means?
Okay. Perfect. Thank you. I had a question.
Okay.
Thank you.
I will put that. Oh, yes. We actually did that this morning too, but I'll do this as well.
Thank you.
Question about lab.
Yeah.
Did the first get announced which labs were due?
Yeah, I put that on Canvas.
Okay.